Welcome everybody. This is lesson 3.2.2, and in this lesson we're going to look at the transformations of logarithmic graphs. Example 1.
Okay, for this question right here, we're being asked to identify which of the following expressions here are exponential. Now, it's important to remember the definition, okay? The definition of the independent of an exponential function is that, okay, take up here the independent variable, okay, which for us in almost every case is the x, is in the exponent. That's the whole point here, okay? So let's take a quick look here. Maybe what we'll do is we'll zoom in a little bit on these things. So y equals 3x to the 8. Is that exponential? No. No. In fact, this is polynomial. Okay? The x is in the base. So by definition can't be exponential. Right here. Y is equal to 0.5 to the power of x? Yes. Because the x is in the exponent, that is definitely exponential. Y equals -5 to the x? No. Okay, now this is where somebody might get mad at me and say, well, wait a minute, you just said, blah, 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 independent variable is in the exponent, independent variable is x. There it is, in the exponent. Yeah, I know. However, because the base is negative, okay, let's write this down. Base is negative. We run into difficulties here because if x, and remember, x is an element of the reals in this case. That's the idea, that this function extends forever. The domain for an exponential should be all reals. So because x can take on all real numbers, at some point, for example, x is going to be 1/2, and then this will force us to take -5 to the 1/2, or the square root of -5, or let's say the 4th root of -5, and so on. So what's going to happen here? This is going to lead to imaginary results. So this ends up being a complex function, okay? Something that's outside the bounds of the course right now. So no, okay? We have to go up here and we have to amend this. The base, okay, is positive. And actually, we might even say a little bit further here, is positive and not 1. Now, it has to be positive in order for this to work. But if it's 1, it's just boring. It's just 1 to the anything is just 1. It's just not doing anything. Anyway, let's keep looking here. We've got 4 to the x minus 1 over 2. Yep, there's not a problem with that. That is exponential. And then 1 over 5x. Again, the x is not in the exponent here. It's in the denominator. So no, this isn't, what we might say is this is rational. That's probably the best we can state there, is that that's going to be a rational function.
Example 2a.
Okay, now for this question, we're starting to really move towards logarithms, okay? In fact, we're going to need a logarithm to solve this here. Determine the inverse of each of the following. So here we go. The first one is y equals 8 to the x. Okay, well, to get the inverse, what we got to do here is we got to take the independent variable and the dependent variable, and we got to swap them. Okay, if you think of a function as kind of a machine that has an input and a corresponding output, then what we're doing is we're running the machine in reverse. Our output is now becoming the input, and we're going backwards here. And so that's how we do this here. So the inverse of this is going to become x equals 8 to the y. Now, this is, okay, this is the inverse. Okay, you can't see that, but let's pull that back just a little, back just a little bit. This is the inverse. Okay, that doesn't require anything else to be the inverse. Just swapping the x and the y creates the inverse. However, this is not typically how we represent this kind of relationship in our formal math notation. So what we're going to do here is we're going to isolate the y, and to do that requires the use of a logarithm. Okay, so the y is in the exponent. We are going to isolate the y. We're going to tell you what y is equivalent to. but y is in the exponent. I'm going to keep going back to that. So y is going to equal the log base 8. Okay, the bases are the same. Okay, because the expression that I'm giving you is identical to this one, so the bases are the same. And in this case, it will be the log base 8 of x. So this is an exponent. A logarithm, therefore, because of where y is up here, a logarithm is an exponent. And there we go. Y equals log base 8 of x.
Example 2b.
All right. So for this question here, again, we're trying to find the inverse, but this time we're looking at a logarithmic function here. So same sort of thing. What I got to do first of all is I have to swap the independent and dependent variables. Okay? So in this case, that's going to take y equals log base 12 of x, and that's going to make that x is equal to the log base 12 of y. Okay, and remember, right now, this is the inverse. Okay? This is the inverse of the original function. But we don't write it like this. We want to have y isolated. So what I got to do is I got to convert this to the other form, the exponential form of this. Okay, remembering that a logarithm is an exponent, and that I've got another form that preserves the same relationship here. If the base is 12 here, then the base of my exponential function is going to be 12. So y is going to equal an exponential function base 12 to the exponent of x, and I know that because the logarithm is an exponent. So y equals, so I might write it like this, therefore y is equal to 12 to the x.
Example 3a.
Okay, well here's a good question. A lot going on in this question. So we're going to identify the properties of the following functions given the original function, y equals the log base 5 of x. Okay, so we are given that the new function here is negative log base 5 of x minus 13 plus 2. First thing we're asked to do is identify the transformations. And that's a good thing to look at first because that influences all the rest of this material here. So the first thing we're seeing here, okay, that negative, that is a vertical reflection, okay, over the x-axis. Okay, now remember, I know that because it sits out front of the function. Okay, the original function was the log base 5 of x. This sits out front. This represents the dependent variable, and now it's become negative. It's flipping. Okay, I move inside. There's no coefficient of the x, so there's no horizontal reflection or stretch. However, I've got x minus 13, meaning that there's been a horizontal translation 13 to the right. That's happening within the function. That is a change on the independent variable. Now, outside the function, okay, remember this is the original dependent variable, the log base 5 of x, and I'm increasing that by 2. So now there's been a vertical translation, okay, of 2 up. All right. Now, bearing in mind what a logarithmic function looks like, okay? So when we started off with y equals the log base 5 of x, okay, that is going to look something like this. Okay, going through 1 there. The vertical asymptote here was at x equals 0. It's a vertical line at x equals 0. Now let's just think about this. A vertical reflection over the x-axis. Okay, this is a vertical, think of it like this. Here's my vertical line, vertical reflection. Won't change it. Horizontal translation, 13 to the right. Okay, now that will change it. Okay, we take this line, we move it 13 to the right. Was it 0? Now 13. Now, moving it 2 up. Now just think about this line if you moved it 2 up. If I had done the vertical translation first, well, that's not going to change the horizontal line there. I mean, the vertical line there. So, my vertical asymptote will only be affected by the horizontal translation, and that is now going to make this x equals 13. Okay, now the intercepts, because we're being asked for the x and the y intercepts. Let's take a quick look at the x intercepts. Okay. Now, x-intercepts occur where the y-coordinate is equal to 0. So I'm going to write that in. 0 is equal to negative log base 5 of x minus 13 plus 2. Okay, maybe what we'll do here is we'll zoom in a little bit on this. Now, finding the x-intercept always involves the creation of an equation that needs to be solved. So on the right-hand side of the equation here, I've got two terms. Only one of them has the independent variable in it. So I need to move that constant over, that 2. So it'll become minus 2 is equal to negative log base 5 of x minus 13. Now I want to move my way in towards the x here. I've got a coefficient though, a negative coefficient, so I'm going to bring that over to make that positive 2 log base 5 of x minus 13. Okay. Now I've got the logarithm isolated here. So to solve this, what I need to do is convert this into exponential form. So the base is 5. The logarithm is an exponent, so this becomes 5 squared will equal the argument of the logarithm. So it's going to equal x minus 13. Okay. Well, 5 squared is 25. And when I bring the 13 over, I will get 38. So my x-intercept here is 38. Now, that's my x-intercept. My y-intercept is actually a substantially easier thing to do here. The x-intercept involves the creation of an equation, whereas the y-intercept is actually just about evaluating. So this will be the log base 5 of 0 minus 13 plus 2. Okay? Now, 0 minus 13 is going to be negative 13 plus 2. And now we immediately run into problems here because, look, I cannot take the log of a negative. Okay, I'm not allowed to. There's a restriction there. At least not until you get to university here and then you start looking at complex numbers. But for right now, can't do that. So we write this out here. There can be no y-intercept because we can't find the log of a negative. Okay, that is outside the domain of the negative. And actually that makes perfect sense when you think about it. We took this graph right here that had a vertical asymptote at 0 and we moved it 13 to the right. We moved it away from the y-axis. Okay, so up here, y-intercept, well, it turned out there was none. Okay, now let's think about the domain. Well, just like I had said before here, that the whole graph here has been moved 13 to the right. The domain is going to be linked to the asymptote. Now, this graph has not been reflected horizontally, so if you remember what a logarithm looks like, it's going to swoop out to the right here. So this is still going to swoop to the right, but it's going to be to the right of 13 because the whole graph is moved over 13 units. The range, well, none of these translations is going to change the fact, that the range is simply going to be an element of the reals. And since we've identified the transformations here earlier, identifying the mapping is pretty straightforward. It's just a matter of interpreting that. We have moved the thing 13 units to the right. There has been a vertical reflection and a vertical translation 2 up. And there you go. A lot going on in this question. Good question.
Example 3b.
All right. Basically the same question as the one that we just did, except this time, slightly different function. Negative log base 5 of 1/5 x plus 25. Now, before we can do anything to this, in terms of identifying the transformations, and that's really where I want to start, but I got to make this so that I can see the transformations clearly, and I can't when I can tell that that horizontal stretch has been multiplied through or been distributed to the translation. So what I got to do here first is factor that 1/5 away here. Now be really careful. This question is set up, designed specifically to suck you into an error. Okay, 25 divided by 1/5 is 125. Okay, I suspect the majority of people, when you first look at this and you think, oh, that's easy, I'm just dividing by 5. So this should be 5 here, but you're not. You're not dividing by 5, you're dividing by 1/5. And when you divide by 1/5, you have to multiply by the reciprocal, and that's what takes us up to 125. Okay, distribute the 1/5 back through and see. Okay, when you multiply 1/5 by x, you get the 1/5 x, 1/5 by 125, that's what gets you the 25. So now my transformations, looking at this from the left-hand side to the right-hand side, first thing that we bumped into is a vertical reflection. Okay, over the x-axis, followed by, now we move inside the function. This 1/5 is an adjustment to the independent variable, so this is a horizontal stretch. Okay, by a factor of 5, because remember we reciprocate that. And then the only thing left here is this 125, but again, it's been added to the independent variable, so this is going to be a horizontal translation. Okay, 125 units left. Okay. Now, let's think about which of these is going to change the vertical asymptote, because that's the first question we're being asked here. Okay, well, a vertical reflection, remember, the vertical reflection will not affect a vertical line. It's just going to flip it like this. Now, a horizontal stretch also will not change this. And the reason for that is because when we start talking about y equals the log base 5 of x, the original function here, okay, that asymptote there, that vertical asymptote is the y-axis. Under a horizontal stretch, okay, for a horizontal stretch, the invariant points are on the y-axis. So that horizontal stretch is going to have no impact on that vertical asymptote. The only thing that will is a translation 125 units to the left. And so that means our vertical asymptote is going to be x equals negative 125. Okay. Now let's take a look at the x and the y-intercepts. For the x-intercepts, as we did in the previous question, we're going to create an equation by making the y equal to 0. Now I'm going to use my adjusted equation here. I'm going to use the one where I factored out the 1/5. Now, what I need to do here is I need to work my way in towards that x. So the first thing I'm going to do is remove the coefficient. There is no other term here. I'm just going to deal with the coefficient. And when you divide both sides by the negative, it just disappears. So I've got 0 is equal to the log base 5 of 1/5 x plus 125. I've got the logarithm isolated, so now it's time to convert this to the exponential. That's how I solve logarithmic equations. So the base is 5, so the base is going to be 5 for the exponential. The logarithm equals 0, so the exponent is 0. And then that is going to equal my argument. 5 to the 0 is 1. And then I'm going to multiply through by 5 to get that denominator out of the way here. So this is going to give me 5 is equal to x plus 125. And then when I bring that over, I'm going to get negative 120 is equal to x. Okay, so there's my x-intercept. Negative 120. Whoops, sorry, you can't see that. X-intercept is negative 120. Now, my y-intercept, as we saw in that last question here, this is just a matter of evaluating. So this is going to be y is equal to the negative log base 5 of 1/5 of 0 plus 125. And all I got to do is evaluate this. Okay, well 0 plus 125, 125. 1/5 of that is going to be 25. The log base 5 of 25 is just 2, and there's a negative coefficient right there. So my y-intercept here is going to be negative 2. Okay, there we go. Now, let's talk about domain. Now remember, the domain, when you look at the original logarithmic function, your domain here is going to be x is greater than 0. Okay. In this particular case, there has been no horizontal reflection here, so that hasn't changed. Okay. It hasn't. It's not that it's opening the other way now. It's still opening the same way. The only thing that's going to affect this is going to be that translation, and it's been moved 125 units to the left here. So now instead of being x is greater than 0, it'll be x is greater than negative 125. As with the previous question, none of these transformations is going to change the fact that the range is all reals. And our mapping, once we have the transformations, our mapping is fairly straightforward. We've got a horizontal stretch by a factor of 5. Okay, we have, sorry, I haven't addressed the most important one here, and that was the translation 125 to the left. And then vertically, all that's going on is that reflection. So there's a negative y there. There's our mapping.
Example 4a.
All right, so in this question, we have to compare the two logarithmic functions that we've been given here. It didn't describe them in terms of their transformations, because again, we're really focused on understanding the graphs right now, and the properties of the functions as they relate to the graphs here. Notice that what changes between these two right here, the original and the one that I've got here, is the base. Now, in order to compare these things accurately, what we need here is we need them to have the same base. Okay? Which means I need my change of base formula. So in this case, I have log base 2 as my original here, and I've got log base 1/8 of x. So what I'm really going to do here is I'm going to take that log base 1/8 of x, oops, okay, and I'm going to change that to a base 2. Actually, here I'll zoom in a little bit. So log base 1/8 of x, if I convert this to base 2, is going to be log base 2 of x over the log base 2 of 1/8. That is my change of base rule. Okay. Well, there's not much I can do with the log base 2 of x. That is what it is. But the log base 2 of 1/8, now let's just think about that. 1/8 as a power of 2. Okay. 1/8, if I want to think about that, 1/8 is going to be equivalent to 2 to the negative 3. So because that's the case here, because I can convert 1/8 to a power of 2, the logarithm is the exponent. So this is going to be over negative 3. And so now I can rewrite this, okay, because there is dividing by negative 3 is like multiplying by negative 1/3. We can write it like this, which means, interpreting what I'm seeing right here, there has been, okay, first of all, a vertical reflection over the x-axis, and then a vertical stretch by a factor of 1/3. Whoops, there we go. There you go.
Example 4b.
So as with the previous question, what we're doing here is we're comparing this, okay, to log base 2. Okay. And again, what I need to do here to make an accurate comparison here is I need to see this as, to have this as the same base here. So what I got to do with the log base 32 of x is I've got to make this the log base 2 of x over the log base 2 of 32. Again, that's the change of base formula. Now, 32, okay, 32 can be written as a power of 2. 32 is 2 to the 5th. So there's really nothing I can do with my numerator. That's fine. But remember what a logarithm does here. This is log base 2. Okay, well, I was able to write 32 as a base 2. So as a result, the logarithm is just going to give me the exponent. And so dividing by 5 is the same as multiplying by 1/5. Oops, so I get 1/5 log base 2 of x, and notice that that 1/5 now becomes a coefficient. So this is a vertical stretch by a factor of 1/5. Oops, sorry, can't see that. Vertical stretch by a factor of 1/5.
Example 5.
All right, with this question right here, this is probably the most straightforward out of the set that we've just done. It's the longest question, granted, but all we got to do here is we're going to take y equals the log base 5 of x, and we're going to transform it using the transformations that are described here. So, having had a vertical stretch by a factor of 4, well, I know that that means I need to multiply, okay, I need to multiply the function by 4. My coefficient out front here needs to be a 4. It's had a horizontal stretch by a factor of 1/5. Okay, so this is now going to be the log base 5 of, okay, now whatever it is I'm taking the log of, okay, in terms of the independent variable here, I need to multiply that independent variable by a factor of 5 here, because my horizontal stretch is going to be 1/5. Remember, whenever we identify that horizontal stretch, we have to reciprocate it. So if I know that the stretch is 1/5, I have to reciprocate it to put it back in. A reflection over the y-axis. Okay, over the y-axis. Y-axis is the vertical one, so over it is this way. That's a horizontal change, meaning that 5 there should be negative. A horizontal translation 15 to the right. Okay, now I need to separate that from the stretch. So here's my independent variable. 15 to the right is going to mean minus 15. And then a vertical translation 11 down means taking that function, which is the dependent variable, and I'm going to subtract 11. And there we go. There's the function that we're describing.